Hi everyone! We're on Module 4 entitled Energy Transformations in Matter. But this video will only discuss the introduction to thermochemistry. At the end of this session, you should be able to define thermodynamics and thermochemistry. Next, discuss the difference between system and surroundings, types of system, state and path functions, exothermic and endothermic processes, energy in transit and stored energy, latent heat and sensible heat, and various forms of energy. Okay, let us define some of the important terms. So what is thermodynamics? So it is a branch of physical science that deals with the relation between heat and other forms of energy, such as mechanical, electrical, or chemical, and the relationship of all forms of energy. On the other hand, thermochemistry is a branch of thermodynamics which focuses on the study of heat given off or absorbed in a chemical reactions, or specifically the study of thermodynamics in regards to chemical reactions. Why study thermochemistry? We depend on energy for nearly every aspect of our lives. Energy is everywhere. It can manifest in many forms. Think about how we use energy every day. In electricity, cooking, automobiles, heating, batteries, body temperature regulation, conversion of food into usable cellular energy, and many other things. Energy is defined as the ability to do work and heat. In chemistry, work is defined as directed energy change resulting from a process. Energy can be mainly classified as potential or kinetic. An object that is moving has kinetic energy and can do work. Molecules moving in space all have kinetic energy. However, any object that is lifted from its resting position has stored energy. It is called potential energy because it has a potential to do work when released. Next, we have the law of conservation of energy. It states that the total quantity of energy in the universe is assumed constant. And this is the basis of the first law of thermodynamics. Here are the energy transformation. You yourself are transforming chemical energy from the food you eat into kinetic energy as you walk, breathe, and move your finger to scroll up and watch this video. Light bulbs transform electrical energy into light energy. And plants convert the energy of sunlight into chemical energy stored in organic molecules. All forms of energy are either potential or kinetic energy. Potential energy is defined as the energy stored by a body by virtue of its position relative to others, stresses within itself, electric charge, and other factors. So the types of potential energy could be chemical energy, nuclear energy, gravitational energy, and elastic energy. Potential energy can be computed using this formula: mass times gravitational field strength and height. Gravitational field strength is Newton per kilogram. That is the same unit as acceleration. and the gravitational constant due to acceleration is 9.8 meter per second square. The second type is kinetic energy. So it's the energy due to the motion of an object. And the types of kinetic energy could be mechanical energy, electrical energy, and magnetic energy. Thermal energy is also kinetic energy. So to compute for the kinetic energy, that is equal to 1/2 mass times velocity of the object square. These are the units of energy. First is joule. It is SI unit of work or energy equal to the work done by a force of 1 Newton when its point of application moves 1 meter in the direction of the force. The conversion is 1 joule is 1 kilogram meter square per second square. Actually, joule is Newton meter. And Newton is equal to kilogram meter per second square. The second unit of energy is calorie. It is the energy needed to raise the temperature of 1 gram of water through 1 degree Celsius. And 1 calorie is equal to 4.184 joules. Third is the big calorie. So it is the energy needed to raise the temperature of 1 kilogram of water through 1 degree Celsius, equal to 1,000 small calorie or the same as 1 kcal. Then last, British thermal unit or BTU. It refers to the amount of energy that is required to increase the temperature of 1 pound of water by 1 degree Fahrenheit. And 1 BTU is equal to 1,055 joules. In discussion of heat flow, it is important to distinguish between system and surroundings. The system is that part of the universe on which attention is focused. So in this picture, the water is heated from 50 degrees Celsius to 80 degrees Celsius. It absorbs heat from the surrounding. And the next figure is when the hot plate is turned off, the system gives off heat to the surrounding and its temperature drops. The system here is a sample of water in contact with hot plate. The surroundings here are the hot plate, beaker holding the water sample, and the air around it. In a chemical reactions, the reactants and product are considered to be the system. And the surroundings include the container in which the reaction takes place, and the air or other material in thermal contact with the reaction system. Everything that is not included in the system is defined as surroundings. The system and the surroundings together make up the universe. There are 3 types of system in thermodynamics. So those are the open system, closed system, and isolated system. An open system can exchange both mass and energy with its surroundings. In this example, the heat and water vapor can be lost to the air. A closed system, on the other hand, can exchange only energy with its surrounding, not mass. Putting a very tightly fitting lid on the container would give us a closed system. An isolated system is unable to exchange anything with its surrounding. A perfect isolated system is hard to come by, but an insulated drink cooler with a lid is conceptually similar to a true isolated system. A very good thermos is another example where mass and energy is insulated. Next is the functions of a system. So there are two functions. First one is state functions. Those are the properties that are determined by the state of the system regardless of how that condition was achieved. These depend only on the initial and final state of the system and not on how the change is accomplished. Example, energy, pressure, volume, temperature, and density. Path functions are properties or quantities whose values depend on the transition of a system from the initial to the final state. Example, work and heat. Heat is not a state function because it is only to transfer energy in or out of a system. It depends on pathways. Work is proportional to the distance an object is moved, which depends on the path used to go from initial to the final state. Heat flow is not a state property. Its magnitude depends on how a process is carried out. The gain in gravitational potential energy that occurs when a person climbs from the base to the top of a mountain is independent of the path taken. So potential energy is a state function. If a quantity is uniquely determined by the equilibrium state, then it is a state function. Okay, work is a path function. So work and heat transfer are not properties. They are the forms that energy takes to cross the system boundary. What is the difference between stored and transit energy? Stored energy is within the boundary of the system, independent of path. They are thermodynamic properties, have unique value for each thermodynamic state. Example, internal energy. Internal energy is forms of energy in the matter due to its internal structure. So it is also called microscopic forms of energy. Another example of stored energy is kinetic energy and potential energy. Opposite to stored energy is transit energy. Transit energy can cross the boundary of the system. It is path dependent. They are not thermodynamic properties. They are the forms that energy takes to cross the system boundary. Examples, heat and work. Heat is a transit form of energy that occurs when there is temperature gradient. And work is a transit form of energy that occurs due to all other driving forces. Almost all chemical reactions absorb or release energy, generally in the form of heat. The process involved in the reactions is either exothermic or endothermic chains. So this example is mercuric oxide is heated. So the reaction is, the decomposition of mercuric oxide at high temperature is an endothermic process wherein energy is supplied to the system. The system here is mercuric oxide, liquid mercury, and oxygen gas. So, an endothermic process requires heat to be supplied to the system by the surroundings. Next is the combustion of methane. The combustion of methane gas in oxygen is one of the many chemical reactions that release quantities of energy. The reacting mixture here is the system. So this reaction is an exothermic process. There is a transfer of thermal energy to the surroundings. In exothermic chains, in which there is a release of energy and heat, it has a lower activation energy. Unlike in endothermic reaction, it has a higher activation energy. How to classify the phase changes as endothermic or exothermic? Energy change accompanies all phase changes. The question is, what kind of change in energy accompanies each phase change? All phase changes that requires the input of heat, like from solid to liquid to gas, are an example of endothermic change. On the other hand, moving from gas to liquid to solid requires the opposite. Heat must be transferred. These phase changes are called exothermic reaction. So a good way to remember all of this is that opposite phase changes have opposite energy needs. So we have here an example: liquid to solid, freezing of water; gas to liquid, water vapor; gas to liquid, the formation of frost. So from water vapor in an above freezing atmosphere, coming in contact with a solid surface whose temperature is below freezing, and resulting in a phase change from water vapor to ice. That is a formation of frost. Then solid to liquid, so that is ice melting. Liquid to gas, boiling water. And solid to gas is dry ice. Dry ice is a solid carbon dioxide which happens to sublimate or turn to gas at chilly 78 or rather negative 78.5 degrees Celsius under normal atmosphere pressure of 1 atmosphere. So because of this, it is useful as a coolant. The reverse process of sublimation is deposition. So that deposition is formation of frost. So in which gas transforms into solid without passing through the liquid phase. So that is how frost form on the ground or other surfaces. Another types of heat are the latent heat and sensible heat. Latent heat is the energy that is absorbed or released during a phase change. So from solid to liquid and liquid to gas and released going the other way. The latent heat energy is absorbed or released at constant temperature. This means the heat energy is used in the breaking of the bonds between molecules during a phase change, but not to heat up the substance. Example, as water freezes, it occurs at a constant temperature of 0 degree Celsius as latent heat energy is released. And the water goes from a liquid to solid ice. So on the other hand, sensible heat refers to heat used to raise the temperature of a substance. So it is also called heat level or heat intensity that can readily be measured when it changes the temperature of a substance. So for the latent heat, so there are three other terms that are important to understand. So we have the latent heat of vaporization, liquid to gas, latent heat of condensation, that's from vapor to liquid, and latent heat of fusion from solid to liquid. This diagram further illustrates the difference between latent heat and sensible heat. The latent heat of fusion for ice is 80 calories per gram. This amount of heat is absorbed by each gram of ice in melting. So ice at 0 degrees Celsius, same temperature, so it becomes ice water. The required energy is 80 calories per gram or equivalent to 334 kilojoules per kilogram, equal to 144 BTU per pound. As the temperature increases from 0 degrees Celsius to 100 degrees Celsius, so there is an increase in temperature, so that is what we call sensible heat. So heat is absorbed, and to raise the temperature of 1 gram of water to 1 degree Celsius is 1 calorie. And 1 calorie is equal to 4.184 joules, which is equivalent to 418 kilojoules per kilogram, or equal to 180 BTU per pound. So at constant temperature, the boiling water will be transformed to steam, so that is the same temperature. So you let it boil. The temperature remains constant, so the water evaporates, and all the heat added to the liquid is absorbed as latent heat of vaporization and carried away by the escaping vapor molecule. So the needed energy is 540 calories, which is equivalent to 2,257 joules, equivalent to 970 BTU per pound. It takes a lot of heat to increase the temperature of liquid water, because some of the heat must be used to break hydrogen bonds between molecules. And because of it, heat capacity, water can minimize changes in temperature. Can you tell me the temperature inside your room? Oh, the temperature is not showing how much latent heat is contained inside the air. When it's really humid inside your room, you probably feel a lot of latent heat in addition to sensible heat. This is the end of this video. If you have questions or any concern regarding this topic, feel free to ask your instructor. Thank you for listening. Bye!